Hi everyone, welcome back to lecture 12 in the series of business analytics course. In this video, I would be specifically explaining the ANOVA table and how the output of Excel data analysis tool pack for regression would look like. So without any further ado, let's get started. So this is how your Excel data analysis tool pack would look like for linear regression. And we are not limited to only Excel. So don't just always assume you will always get from Excel. It could be from any software. It could be from SPSS. It could be from Stata. It could be from R. It could be from Python. But in general, all these software, whenever you process a data set for linear regression, they give you some specific things, and more or less all these things are available in all the software. So what we need to focus on is the concept, right? So let's get started. And as you can see, this is our basic linear regression model, right? Y is equals to beta naught plus beta 1 x1, beta 2 x2, so on and so forth up till epsilon. So just a quick refresher, y is the dependent variable which we are trying to predict. X1 to xk are the independent variables, or you can say the predictor variable or explanatory variable, right? K is the number of independent variables. How many X values do I have, right? How many features I know for each sample point. Beta naught is the intercept. Sometimes it is also known as bias. So yes, both are okay. Beta 1 to beta k are the coefficients for the predictors. They are also known as slopes. And then epsilon is the error term. And then n is the sample size. In the sense, how many rows I have in my data set, or you can say how many sample points I have collected, right? So if I'm doing analysis on 100 student, right, and I have, let's say, their age, their CGPA, number of hours they study, and other stuff. So 100 is basically the sample size because I am doing the study on 100 people. So know this thing. And the number of features, or you can say the number of columns which I collect as feature, are going to be my number of independent variables. So the name, age, and CGPA, and also and so forth. These things are going to be my x1, x2, xk, and what I'm going to predict is going to be y. Then let's see what are going to be my regression statistics. So this is basically the first part of your ANOVA table. This is basically going to give you few important statistic values for your regression. So you can see these things. These are the 5 things which you will see here. So let's just see what these things are individually. Multiple R is basically the correlation coefficient, right? So this is correlation coefficient, and between what? It is going to be correlation coefficient between predicted values and the actual values. Okay. So the correlation coefficient between Y predicted and Y actual is going to be multiple R. For simple linear regression, it is the positive square root of R square. Okay. Now what is R square? So R square is this thing. It is known as coefficient of determination. Okay. It is a key metric in model fit. It is used to assess how good your model is fitting and how good this model is, right? So you can directly compare two models with their R square. So greater the R square, the more we find it useful. Okay. It represents the proportion of total variance independent variable Y that is explained by independent variables X, whatever you have, right? X1, X2 and all. So, the numerator is going to be explained variance, denominator is going to be the total variance, right? So if I have Y and there is a lot of variety in Y, how much can I capture with my X variable, or you can say combination of different X variable, right? So this thing which you see, this is, linear combination of X variable, right? X1, X2 and all combined linearly with each other. So this is what we are trying to know. Whatever model I have built, right? Using that model, how much can I capture the variance in my Y variable? So this is what it looks like, sum square regression by sum square total, which is also equal to 1 minus sum square residual by sum square total. Okay. Adjusted R square I've already explained in the theory part that it is modified version of R square, and it basically penalizes how many variable you are adding in your multiple regression. You can refer to its formula in the theory lecture. Then what is standard error? So standard error of what? So standard error of the regression is basically the root mean square error, and it is basically telling you the standard deviation for your model residuals. So if I calculate variance of this epsilon and then take the under root, this becomes standard deviation of epsilon. This is the same thing known as standard error, and it is also equal to under root of mean square error. So this mean square error which you are seeing here, this is nothing but if you take the square root, it becomes a standard error. So this is the relationship between standard error and the mean square error, which you will be seeing next. And observation, as I said, this is the just number of data points you have. Now coming to ANOVA. ANOVA is basically standing for analysis of variances, and this is how in Excel your data toolpack would look like, your output would look like. So see this thing, this part. So this part which you are seeing here, this is the ANOVA part, and here we will be dealing with degree of freedom, sum squares, mean square, then the test statistic and the p-value. Okay, so let's just go back to ANOVA. So ANOVA stands for analysis of variance, and ANOVA table tests all the significance of the model, right? So for the overall model which we have built, is it useful or not? How do you check this thing statistically? For that, we use ANOVA. It partitions the total variation in Y into two parts. First is the regression, and then another would be residual. Okay. So what is the null hypothesis for this test which we are trying to do? That the model is not significant. Null hypothesis is model is not significant. Important to note, not word here. Null hypothesis is model is not significant. Or you can say all slope coefficients are 0. That means H naught is beta 1 is 0, beta 2 is 0, beta k is also 0. All these things are 0. What would be alternate hypothesis? Alternate hypothesis could be the model is significant, or at least one of the slope coefficient is not 0. Okay. So model is significant, or you can say similarly that implies at least one of the slope coefficient is not 0. So remember this null hypothesis. This is very important. Then coming up to the formula. So how do we calculate degree of freedom? For regression, it is the same number of independent variables. So if I am using 10 independent variables, x1, x2 up till x10, that means my regression degree of freedom is going to be 10. That is why if I have k number of independent variable, my degree of freedom for regression is going to be k. Similarly, degree of freedom for error is going to be n minus k minus 1, right? And then the total degree of freedom is going to be n minus 1. Okay, I hope you remember the concept of degree of freedom, which I explained in week 1 or week 2 for the chi-square goodness of fit and chi-square test of independence. So we are removing this one because we are estimating y bar. So if I have 100 data points and I know y bar of it, so only 99 can be free. The last one has to be fixed, right? So that is why this total degree of freedom is n minus 1, because we are estimating y bar and x bar. So that is why. Now sum of squares. So what is sum of square for regression? Sum of square for regression is y predicted minus y bar ka whole square, and you sum for all the data points. Similarly, for residual, it is going to be the actual y and subtract the y predicted. So whole square of that. And then sum square total is yi minus y bar. So basically actual y minus the mean y, and you square it and you add for all the data points. So this is what you have. What is sum square regression? This is variation explained by model, because you this y predicted is what your beta 0 plus beta 1 x1 so on and so forth, right? And what is the unexplained variance? This is the unexplained variance, right? This is what we cannot capture, and this is the total variation in y, right? So this is what we have. Now what is mean square? So for regression, mean square regression is sum square regression divided by degree of freedom. Similarly, for residual, it is the sum square error divided by degree of freedom for error. Okay. F statistic is mean square regression by mean square error, and this is the test statistic we use for the testing part. You remember chi-square test statistic. So whatever test you are going to do, in a similar fashion, every test has a test statistic. Chi-square has chi-square test statistic, t-test have t-test statistic, and f-test has f-statistic. So this is what your test statistic would look like. And what is the significance f? This is going to be the p-value for the test. And why do we need p-value? To check if we can reject the null hypothesis or we fail to reject null hypothesis. So if p-value is less than alpha, we reject h naught. That is why, if you see the null hypothesis was model is not significant. So if you are making a model, you would like that model to be significant, right? So that is why most of the time we want to reject the null hypothesis in the ANOVA, and for that your p-value should be less than alpha. By default, alpha is to be taken as 0.05, right? But depending on your situation, it can change. So read the question, what is your alpha? But whatever be your alpha, your p-value, or you can say the significance f, should always be less than that. So let's just have a look here again. So you see this thing, degree of freedom for regression, because I have three variables, it is 3. Okay. How many degree of freedom for residual? So I had 200 data points, total becomes 200 minus 1, 199. And then this becomes n minus k minus 1. So 200 minus 3 minus 1. So you have 196 here. So this is how your degree of freedom comes. Sum square is coming like this. Mean square comes by dividing these things. So when I divide 5014 this by this, it gives me this. When I divide this by this, it gives me this. So this is how you get mean square regression and mean square residual. Also, just a quick reminder that this mean square error which you are seeing here, 2.76, right? If I take under root of this thing, 2.76, I will get back this one, standard error. Okay. So standard error is under root of mean square of my residual. F statistic, how does it come? I need to divide this by this. So 167, 1671.59 divided by 2.76. This will give me 605 thing. Okay. And this is the p-value. This is something which you cannot compute manually yourself. You will always be given this thing, or it would be coming from a table. So you don't need to worry about this thing. So this is what your ANOVA table would look like. Okay. And these are all the formula. Please read the remarks which I have given. This is very important. And this is again one important thing, that how our this how our mean square error and standard error are related. So standard error, or you can say root mean square error, RMSE, is equals to under root of mean square error or mean square residual. Both are kind of same. Okay. Now coming to the third part, which is the coefficient table, right? And this table is the most important, because if you want to get the equation, right? I have the data, I give data to Excel and it gives out me the output. So how do I write the equation? How do I write y is equals to something plus something x1 plus something x2? How do I write this thing? How do I fill these blanks? So these blanks are filled using this table only. So you see this thing? This is the column which tells you the estimated coefficients. So what is the estimate of intercept? This is the estimate, 4.625. For coefficient, or you can say the beta 1, this is the coefficient. For beta 2, this is the coefficient. For beta 3, this is the estimate. So this column is very important if you want to write the equation. So let's just see, what do we have? This table provides information about each individual predictor, right? Each individual predictor and the intercept in the model. What is the null hypothesis? Null hypothesis is going to be that each coefficient beta j, or intercept, which is a beta 0, or you can say beta 1, beta 2, for each of them I'm performing a separate t-test. Okay. And what is the null hypothesis? The coefficient is not statistically significant, or you can say it is equal to 0. So I can say beta 0 is 0 or beta 1 is 0. Remember, this test is performed individually for each intercept. So if I have, let's say, 10 input variables, x1, x2, x3, x10, right? That means I would be performing 11 tests, 10 tests for these slopes, right? Beta values, beta 1 to beta 10, 10 tests for these things, and then one test for beta naught. So remember, if I have k variables, I would be performing k plus 1 t test. Okay. And what is the alternate hypothesis? The coefficient is statistically significant, or you can say it is not equal to 0. So this is what your null hypothesis and alternate hypothesis look like. And again, you can see this thing. The first column is for coefficients. Coefficients is basically the intercept value for your estimated value for intercept and the slopes. Then you have standard error. So what is the standard error for each of these estimated coefficient? You can see this thing here, right? So if my intercept is estimated to be this, there is still some standard error, right? So this is what it looks like. So standard error for each individual coefficient, it measures the uncertainty in the estimate of that coefficient. What is t statistic? T statistic for individual coefficient is calculated by this thing. So the estimated by standard error. This is going to be your uh, t statistic. Okay. So always remember the formula. F statistic was mean square regression by mean square error. T statistic is going to be estimated coefficient by standard error. What is the p-value? This is again associated with the t statistic. And if this p-value is less than alpha, you will reject h naught. And if you see what is h naught, coefficient is not statistically significant. So you would like your input variables to be significant, right? So generally here also we want to reject the null hypothesis. Therefore, you would want a p-value which is much less than your alpha. Okay. And then this lower 95, upper 95. So this is basically the range for your 95% confidence interval for the true value of coefficient. And remember this thing. If this interval does not contain 0, it is equivalent of having a p-value less than 5, less than 0.05, right? So remember this thing. If your 95% range does not have 0, it means you have rejected the null hypothesis. So if you see this thing, right, lower 95, upper 95, right? So if you see here, every time if I don't have 0 in between this lower to upper, that means I am rejecting the null hypothesis. Okay, so this is what your regression coefficient table would look like. Now we would just again look back at this example. So this is coming from a data set here. You can click and open this thing, and this is the output which you will get in Excel. Okay. You can see this thing, we have 200 variables and 3 independent variables, x variable 1, x variable 2, x variable 3. So basically x1, x2, x3. And from this you can imagine how our equation would look like. Beta naught plus beta 1 times x1, beta 2 into x2, beta 3 into x3 plus epsilon. So this is what our linear regression equation looks like. Now you can see this thing, r square is this. It tells us, that it is a very strong fit because r square is very high. You can look at here, r square is 0.90, or you can convert it into percentage, that becomes 90.11%. That means 90% of my variance in y, let's say this is my y, this is the variance in y. I can explain this variance 90% of this using the x variables which I have, x1, x2, x3. So this is what it says. You see, it indicates that 90.26, what do I have? Oh yeah, this is 90.26, correct. Sorry, not 90, that was adjusted r square. So it indicates that 90.26% of total variation in the dependent variable y is explained by 3 independent variables, x1, x2, x3. Or you can say the linear combination of these 3 variables, right? Then what is the standard error? Standard error is that 1.66. So on an average, model prediction are off by about 1.66 units of y. So if my equation line is like this, so you can imagine my predictions would be on an average 1.66 off from this line. Now the section 2 of ANOVA, right? What was the hypothesis? All the slope coefficients are 0. Null alternate was at least one is not 0. This is my test statistic, 605 30.38, and this is my significance F. So how do I reject or do I fail to reject? So you look at this thing. What is this? This is my p-value. By default, as I said, we will assume 0.05 as my alpha. Is my p less than alpha? Yes, very much. This is very small value. That means we can safely reject the null hypothesis. So you see this thing, this is my test statistic and this is the significance F. You see this thing, the number is this, which is very small. Therefore, we can reject the null hypothesis and we conclude the regression model is statistically significant. At least one of our x variable is meaningful predictor of y. Okay, this is, remember this thing, that this is for at least one. So maybe I am doing analysis for 5 variables. Out of 5, maybe 2 are not significant, but still this test will say overall model is significant because at least one of the variables, right, is going to be significant. Then coming to the coefficients part, these are for the intercept. So p-value for intercept is this value. You see, this is the estimated part and this is the p-value. So if you look here, p-value is 1.68 to the power into 10 to the power minus 34. So this is also practically 0. All these things which you are seeing here, these are practically 0. And since p-value is less than alpha, we can reject null hypothesis. And what was our null hypothesis? If you see here, in the coefficient table, null hypothesis is, the coefficient is not statistically significant, right? It is not. So this is what we want to reject, because for the first 3, intercept x1, x2, we can see p-value is less than alpha. For these 3, we can reject null hypothesis. We can say intercept x variable 1 and x variable 2. These three are important. These three are statistically significant. But for x variable 3, if you see, p-value is 0.95, which is quite higher than 0.05. So therefore, for 3, we will fail to reject null hypothesis. So you can read this thing here. For x, we can say intercept, it is significant. X variable 1, it is also statistically significant. X variable 2 is also statistically significant. And x variable 3, you see this thing, p-value is this. Therefore, it is not significant. We fail to reject null hypothesis. This variable does not add statistically significant predicting power to the model, given that x1, x2 are already included. So this variable is, kind of extra variable, and we can very easily exclude this variable from our model. And if you check the, interval check, let's go back and let's have a look at the example. You see, it is from minus 0.011 to positive 0.011. So basically, I have 0 in between. That means my beta 3 could take a value 0. And that is what I don't want. Therefore, if I see 0 in between this range, I can safely reject that variable. Okay. So remember this thing as well, because sometimes they don't give p-value, but they will still ask you, is this variable statistically significant or not? And then this is our final summary. So based on whatever you can see, our model is the excellent fit because it had a very high R square. And then you can see this thing that variable 1 and 2 were significant, but x variable 3 is not, right? Because you saw that thing. So if you want, you can actually exclude that thing. You can have this much model only, but if you want to include it, you can also include it. So this is what your overall equation looks like. How I have written this thing is coming from my coefficients part. So these all beta 0, beta 1 up till beta 3, they are coming from this part. So this thing which you are seeing here, this is that. This is my beta 0, this is my beta 1, this is my beta 2, and this is my beta 3. Okay. So these 4 values I'm using to write down my equation here. So I hope you enjoyed the video, and I think it will be much more clear when we do some numerical examples. But it's very important for quiz 2. So please, please, please pay attention to this ANOVA table, because there would be definitely few questions coming from it. And what you should know is that, what are the null hypotheses, when do we reject the null hypothesis, and what are the coefficients, because they will give you this table and they will ask you, what is the predicted value when x1 equals to this, x2 equals to this, x3 equals to this. So they want you to predict it. So how can you predict it? You will have to construct the equation from here, right? Or maybe they can blur out something. So then you will have to do the work, right? If I blur out this thing, maybe I can calculate the coefficient from standard error and t-statistic. So these all the relationships and formulas which you are seeing here, please remember them, and remember the relationship in words as well, because that is also very important. So that is it for the ANOVA table explanation. I hope you liked it, and the next video is going to be on the PYQs. So thank you so much.